Hello students, and welcome to a lesson on vectors and its applications. And before we get into all the applications, let's define what a vector is. So first, a vector is an ordered pair of real numbers, A, B. And you'll see in some textbooks the notation for vector, they'll write the V bolded, and sometimes they'll write it the V with the arrow on top of it, and they mean the exact same thing. Okay. And the numbers A and B are components of the vector. And A is the horizontal component and B is the vertical component. In other words, if you look at a vector, it's got two numbers in it. One of the numbers describes the horizontal movement of a certain object, and the other number describes the vertical component or movement. All vectors have a magnitude and direction, which means that a magnitude basically tells you how much. So I'll make a note here. A magnitude basically says how much. Okay. And direction, of course, says where is it headed. Kind of answers those two questions. This is just layman's terms here. I'll define this more rigorously later on, and we'll see some really good. So this first example here asks us, give the magnitude and direction of vector v, which has components 3, 4. So keep in mind that 3 here is the horizontal component, so we can sketch this out, 3. 4 here is the vertical component, so we sketch this out. This has a length of 4. And that means the vector then can be represented using an arrow. So that's vector v. And the magnitude is the length of the arrow. So we use this notation here, absolute value of vector v, that's the same thing as magnitude. And if we want to find this, it's not too difficult, we just use the Pythagorean theorem. And it's, in this case, it's square root of 3 squared plus 4 squared, which equals 5. And I'll make a note here that a magnitude is always positive. Magnitude is always positive. Now, the individual components of this can be negative, but the magnitude is always a positive number. And now we need to look at and find the direction. Now keep in mind that this is just a quick reminder that the direction is in fact the angle measured from the positive x-axis going counterclockwise. So remember that the direction from the positive axis going counterclockwise. So whatever, this is theta right here. And so since we don't have a positive x-axis yet, we can certainly sketch that in. And we're looking for this angle right here, theta. And we can use a tangent ratio. We can use the tangent of theta is equal to 4/3. That means theta is equal to the inverse tangent of 4/3, which is approximately 53.13 degrees. So we're using degrees in this problem. And so we have now uniquely identified this vector as something that has a magnitude of 5 and is pointed in this direction. And when I say this direction, what I really mean is if you start from the horizontal and you rotate it counterclockwise, you're going to rotate it 53.13 degrees. Okay. Let's take a look at another example. So here we have 2, 7. Well, we can do the same thing. This is 2 to the right, 7 up. So we can figure out the magnitude of u is equal to the square root of 2 squared plus 7 squared, and that's the square root of 53. Okay, we can also round that if we're required to, but for right now I'm going to leave that alone. And then theta is this angle there, so tangent of theta is equal to 7/2. Theta is equal to inverse tangent of 7/2, and that is going to be approximately 74 degrees. So nothing too crazy or complicated there. Now let's look at a couple more examples here before we move on to the complicated problems. So here we have an example where everything is kind of a little bit reversed, where we are given the magnitude and the direction, and we're asked to find the component form. So one of the things I'm going to do here is just draw a picture. Usually helps. 25 degrees rotated counterclockwise from the positive x-axis is approximately here. That's 25 degrees. The magnitude, which is the hypotenuse of our soon-to-be formed triangle, is going to be 12. And now with that scenario, with what I have going on so far, I can draw these lines here, and I'm looking for B and A. And I can just solve this using cosine and sine. So you can see that the cosine of 25 degrees is equal to the adjacent over the hypotenuse. So that gives me A over 12. That means 12 cosine 25 degrees is equal to A. And then I can also do the same thing for B. Sine of 25 degrees is equal to B over 12. Thus, 12 sine of 25 degrees is equal to B. And I can, if I need an exact answer, the best I can do is say 12 cosine of 25, 12 sine of 25 degrees. If I needed to round, well, I just evaluate it, and this is approximately 10.88, 5.07. And both of these answers here are fine. It depends on what the situation is, what it is you're expected to do. So this is similar to the previous problem, but this time I have an angle of 200 degrees with a magnitude of 17. So if I rotate 200 degrees, that's down here. 200 degrees, and the magnitude here is 17. And there's two ways I can solve this problem. I can solve by forming a triangle. So I can take this triangle in here. Now I know that if the whole rotation up to this point is 200 degrees, then the angle in here, that little angle right there, has to be 200 minus 180, which is 20 degrees. So I can do, I can redraw this triangle here so it looks a little bit less cluttered. This is 20 degrees, this is 17. I'm looking for A and B. And keep in mind that in this picture, because it is in the third quadrant, A and B are negative. So I can solve this problem the same way I did before. I just have to be careful with my negatives and positives. So I know that A is going to be 17, not 12, cosine 20 degrees. B is going to be 17 sine 20 degrees. Okay. And again, they have to be negative. And it's going to come out to be negative 15.97. And approximately, this is approximately negative 5.81. And this is certainly a good answer. Now, here's another way that I can approach this problem. Let's see here, running out of colors. So here's another way is just to take advantage of what we already know about sine and cosine and trig ratios of large angles. We don't necessarily have to draw this in. If you remember back to the unit circle, anything that is in here, another way, anything that is in here is negative x and negative y. Okay, so you could have also just done 17 cosine 200 degrees and then 17 sine 200 degrees. and that'll give us the exact same result, because the negative is sort of taken care of by this angle right here. This big angle here, you know it's going to have a negative x and a negative y. So you know, if you see this problem for the first time, you may struggle a little bit. Feel free to draw out the triangle, but hopefully in the long run you can see this image and be able to just use cosine and sine even with an angle that is greater than 180 degrees. Okay. So I'm going to end this video here. This is this is the end of the beginning, end of our introduction. We are going to move on to some more challenging and difficult problems in the next videos.